So in this question, we're asked to evaluate the integral that we see here. And the first thing that I'm going to recognize when I look at this integral is that it's a rational function. So all that means is that the top line and the bottom line are both polynomials. So the next thing that we need to think about is the degree of the polynomial on the top line and the polynomial on the bottom line. So looking at this one here, the degree is the highest power that we have. So that's going to be the little 3. Right? So that means that our numerator has a degree of 3. And the bottom line here, looking at it, the highest power, it's going to be like x to the power of 1. Okay, so we can see that the top line has a higher degree than the bottom line. So what that tells us is that the first step we need to perform is polynomial long division. And that's so that we can make the top line have a degree which is smaller than the bottom line. Alright, so let's go ahead and do that. Right here, long division. Alright, so setting it up, inside this little symbol, we're going to put whatever's on the top line, so x cubed 2x squared minus x plus 3. And outside on the left here, we put whatever we're dividing by, which is x plus 1. So now what we're concentrating on is the highest power that we have on both parts. So the highest power we said was x here, and the highest power we have here is x cubed. Alright, so we need to figure out how many times x goes into x cubed, and I would say the answer would be x squared. Okay, x squared times x gives us x cubed. So the next step in our long division is to take whatever we've just decided and multiply it by whatever we're dividing by. So x squared times x gives us x cubed, and x squared times 1 just gives us x squared. And we want to take that away from what we had. Okay, so x cubed minus x cubed is going to leave us with 0, so I won't mark that in. But 2x squared minus x squared, it's just going to leave us with an x squared on its own. Alright, so I'm going to carry down everything else that we had on this line, because it's like x minus 0 leaves us with that minus x, and 3 minus the 0 that we would have here leaves us with the 3. Alright, so now we're going to repeat this process where we look at our highest power, and this is our new highest power. So the number of times that x goes into x squared, it's just going to be x. Okay, so now we take the x and we multiply it by what's over here. So x times x gives us x squared, x times 1 gives us just x. And again, we want to take it away. So x squared minus x squared leaves us with 0. And then we've got x minus x, that's going to leave us with negative 2x. And again, we're going to bring down this 3. It's kind of like 3 minus nothing, leaves us with that 3. Alright, so, and again, we're looking at the x here as our highest power, and now the negative 2x is our highest power. So the number of times that x goes into negative 2x, I'd say that is negative 2 times. So now let's go through and do the multiplication. So negative 2 times x is negative 2x. Negative 2 times 1 leaves us with negative 2. And again, we want to take this away. So I've got a few negatives to contend with this time. So it's negative 2, and then we've got a double negative here, which makes it positive. So negative 2 plus 2x, that's just going to leave us with 0. It all cancels out. And then we've got 3 minus negative, so again plus the 2. 3 plus 2 is 5. Alright, so that's as far as we can go. This is like our remainder that's left over, okay, because we're not going to be able to put x into 5 at all. So put here remainder 5, and it's going to be in our interest to write this in terms of a fraction rather than in terms of just a remainder. So our answer would be, if I come down here, it's going to be x squared plus x minus 2 plus our remainder, we can write it as 5 over whatever we were dividing by. So that's going to be the x plus 1. Alright, so this is equal to this version. So what I might do is put our little integration symbol in and move our little dx down so that it tells us we're integrating with respect to x. And what we're going to find is that this one we can actually just integrate straight away because it's simplified to something that's 5 over x plus 1 in terms of like the fraction part, which is something that we can already integrate using our integration by substitution rules. So let's go ahead and actually evaluate this. So these first 3 terms are pretty easy. We're going to be able to use our power rule where we add 1 and divide by the new power. So adding 1, it's going to be x to the 3 divided by 3. This one, when we add 1 to the power, it's going to be 2 over 2. And this one, it's just going to get an x. So the only kind of tricky one is this 5 over x plus 1. And if you remember the pattern, you can apply it. Otherwise, you can try your integration by substitution technique. So let me just isolate this part for us. Alright, so if we're going to apply our integration by substitution, we need to let u equal the inside function. And I would say my inside function is going to be whatever's on the bottom line. So the x plus 1. And I need to take the derivative of it with respect to x. So the derivative of this is just going to be the 1 in front of the x, and the constant drops away to nothing. So we want to make this into dx equals, so we can sub it in back up here. So if I rearrange the equation, which is basically moving the dx up, we get du equals dx. So we can rewrite this. So 5 over, we've said this bottom line is now equal to u, and we know here that dx is equal to du. So we can sub it out. So now we can apply our rule where the integral of like 1 on x would be the natural log of x. So here the integral of, we've got it as basically like 5 on u, be 5 times the natural log of u. And we don't really want to answer this in terms of our random variable that we introduced u. We'd prefer to have it back in terms of x. So we have that relationship, so it's just a matter of going back and popping it in. So we're going to get 5 times the natural log of x plus 1 is the integral of this term here. Cool. And the very last thing that we need to remember is that we've done like an indefinite integral here. There's no bounds. So we're going to have a little plus c on the end holding the place of the constant. So that there is the answer to this particular question.